The real shift this week is that reasoning is becoming something you can times, steer, allocate, and price. Times, not just scale. One line of work shows that what makes models like O1 and DeepSeek R1 smarter is the structure of their post-training data, not just more tokens. Another turns inference into a controllable token budget problem. And a third treats reasoning compute like an economic resource with a shadow price. Stick around, because the interesting part isn't that these models think harder, it's that we're learning exactly when thought is useful, when it's wasted, and how to make every token count. Let's explore the first paper, a primer in post-training reasoning data, what we know about how it works. A primer in post-training reasoning data, what we know about how it works, is a survey from Peking University, Tsinghua University, and Guiyuan Tech that synthesizes more than 150 public studies to explain why post-training data, not just optimization, drives reasoning gains in systems like OpenAI's O1, style models, and DeepSeek's DeepSeek R1. The paper argues that reasoning data should be treated as verifier-bearing records, not simple prompt-response pairs, and organizes the field around a verifier-anchored taxonomy with 3 contracts: programmatic verification for math, code, and lean-proof corpora, environmental verification for tools, web, app, and software agent trajectories, and judgment-required verification for safety, medical, and rubric-based tasks. Its main novelty is an attribution framework. Quality depends on where supervision enters the trajectory, whether labels are outcome-only or step-level, how behavior is bounded, and what lineage is inherited from teachers, filters, and self-play anchors. The authors emphasize counterintuitive findings, such as long chain of thought traces, not implying faithful reasoning, hard examples being useful only relative to a base model and verifier, and clean successful agent transcripts, erasing the failures and retries needed for credit assignment. They also separate scaling into reachable ceiling versus efficiency, showing that data uniqueness, verifier refresh, search topology, and inference time budget can change measured capability without meaning the model itself improved. Let's explore the second paper, Agentic Chain of Thought Steering for Efficient and Controllable LLM Reasoning. Agentic Chain of Thought Steering, or ACTS, from University of California, San Diego, and Intuit AI Research, reframes LLM reasoning control as a Markov decision process in which a controller agent steers a frozen reasoner step by step under a thinking token budget. Instead of only shortening or truncating chains of thought, ACTS chooses an explicit high-level strategy: understand, plan, execute, explore, check, summarize, or conclude, plus a short natural language steering phrase that opens the next reasoning step, preserving generation continuity while making inference time control explicit. The controller is initialized from synthetic steering trajectories extracted from OpenR1, math traces generated by DeepSeek R1, then improved with multi-budget supervised fine-tuning and GRPO reinforcement learning using budget condition reward shaping that penalizes both overthinking and premature termination. Across math, 500, Amy24, AMC, Olympiad Bench, and GPQA Diamond, ACTS matches or beats vanilla full thinking baselines while cutting tokens by 34.6% to 64.1% on DeepSeek, R1, Distill, Quen, 1, 5, B, and 19.8% to 57% on Quen 3, 8B. On GPQA Diamond, it reaches 30.1% accuracy with 59.5% fewer tokens on the 1.5B model and 46.8% accuracy with 47.7% fewer tokens on the 7B model. The method also transfers to a different model family, Quen 3, 8B, and to Science QA, showing that structured steering can suppress long, confused traces without collapsing reasoning depth. Let's explore the third paper, the shadow price of reasoning economic perspective on optimal budget allocation for LLMs. The paper, from researchers at Zhejiang University, Tencent HY team, and Peking University, reframes LLM inference as a constrained economic allocation problem, rather than a per-query decoding heuristic, using Quen 2, 5, Math 7, B, and Quen 3, 3, 0, B, A, 3, B. Instruct as frozen backbones, the authors show that reasoning utility follows an shaped compute utility curve with 3 phases: strict, surge, and ample. They model each query's latent utility as a shifted surge function with threshold tau, initial velocity alpha, and decay beta. Then solve the batch level optimization with a global shadow price lambda that equalizes marginal utility across active queries. This yields a closed-form token allocation via the principal branch of the Lambert W function and a plug-and-play system called Clear, which combines threshold prediction with bisection-based market clearing and rational abandonment for queries whose expected surplus is negative. On mixed reasoning streams built from Math 500, AMC 23, AIME 24, AIME 25, Minerva, and Olympiad bench, Clear consistently improves the cost accuracy Pareto frontier. At a 256 token budget, it raises accuracy by 11.6 points on a balanced stream, 24 points on mostly easy traffic, and 14.2 points on a U-shaped stream, reaching up to a 3 times gain in global accuracy over uniform allocation in the most resource-scarce settings. The same allocation principle also transfers to code generation, improving Human Eval Plus, MBPP Plus, and Big Code Bench by 3.6 to 6.5 points over uniform budgeting. That's a wrap on today's AI paper highlights. Thanks for watching.